Now I would like to begin the KAIST Research Day 2023. Good morning, my name is Chung, MC for today's event. I would like to extend my deepest appreciation to everyone who joined us here today despite your busy schedules. This year marks the 8th anniversary of KAIST Research Day. Today's event was arranged to thank all the researchers who have made great endeavors day and night, as well as sharing outstanding research achievements of professors who will be giving presentations today. This year's event is all the more meaningful as we are able to gather here in person since the outbreak of the COVID-19 pandemic and congratulate the achievements together. Today's event will be uploaded on the YouTube, and I look forward to sharing excellent research topics and contents that KAIST discovered and engaging in lively discussions. First, I would like to invite Sang-Yup Lee, the Vice President of Research at KAIST, to pronounce the opening of today's event. Mr. Senior VP, please come to the stage.
네, 안녕하십니까.
Good morning.
날씨도 좋고
It's a very good day, and I guess it is a very cheerful day for the students as well. Today, I would like to pronounce the opening of the KAIST Research Day 2023. Please give a big round of applause. Next is Pledge of Allegiance. I would like to ask everyone to stand up and face the flag. Salute the flag.
나는 자랑스러운 태극기 앞에 자유롭고 정의로운 대한민국의 무궁한 영광을 위하여 충성을 다할 것을 굳게 다짐합니다.
At ease. We will skip the singing of the national anthem. Please take your seats. Next, I would like to invite Byung-Kwan Cho, the Vice President of Research, to go over the award-winning selection process. Mr. Vice President, please come to the stage.
So today is a day with a lot of festive occasions that we need to celebrate today. So I would like to give you some background of the selection process and the criteria for selecting the award winners for today's research day. I have a prompter, and they asked me to just read the prompter, so I'm just going to go on and read it. Good morning, I'm Byung-Kwan Cho, VP of the Office of Research Affairs. This year marks the 8th anniversary of KAIST Research Day at KAIST. And during this event, we encourage and acknowledge the dedication of exceptional researchers by giving awards and rewards. It is also an opportunity for researchers to present their outstanding research topics, fostering a sense of pride and achievement. Let us celebrate and enjoy this festive occasion. Before the award ceremony, I would like to give some background of the criteria for selecting commendations in the research category and the top 10 representative research achievements of 2022 in celebration of the 52nd founding anniversary. And during the selection process, we considered many research performance evaluation indicators, including the research contracts, overhead cost inclusion, IPRs, and royalty income. And after a due deliberation by the research committee, Professor Hee-Ta Kim from the Department of Chemical and Biomolecular Engineering was chosen as the recipient of the Grand Research Prize. The research prize was determined based on the research performance over the past year. As a result, Professor Pil-Seung Lee from the Department of Mechanical Engineering and Professor Hyung Myung from the Department of Electrical Engineering have been selected. The Innovation Prize recognizes faculty members who have made significant contributions to innovation in related industries through technology transfer and commercialization. And After considering indicators such as foreign patent registrations, technology transfer contracts, income from technology fees, technology consultations, and startups in the past year, Professor Hyunmin Bae has been selected. The Convergence Research Prize is given to a research group that has achieved outstanding research results through joint convergence research in the past year. After recommendations from colleges and deliberation by the research committee, the research team consisting of Professor Yong-soo Yang and Professor Sang Woo-han and Professor Sung-hwa Yu has been selected for the groundbreaking work on core shell interface 3D atomic structure and properties at the single atom level. The International Joint Research Award is presented to researchers or research groups who made remarkable achievements through international collaborative research in the past year. After receiving recommendations from the colleges and careful evaluation by the research committee, Professor Song Ho Cho has been chosen for his pioneering work on world's first implementation of next-generation intelligent electronic skin technology in collaboration with researchers from Stanford University and Seoul National University. The Hyunwoo KAIST Academic Award is given each year to recognize a scholar who made remarkable academic achievements with the support of the Hyunwoo Cultural Foundation. Again, the recommendations from colleges and deliberation by the Faculty Reward Committee, Professor Pom Jun Kim has been selected for his leading research in developing a new type of polymer electrolyte material. And this KAIST Creative Challenge Research Award, which was introduced this year as part of KAIST's new cultural strategy for the next 50 years, recognizes researchers who have contributed significantly to fostering a culture of creative and challenging research. This award focuses on promoting unique research endeavors and laying the groundwork for pioneering studies, prioritizing originality over conventional excellence. and acknowledges exceptional problem-solving skills and concept validation demonstrated within the C2 project of the research department. Professor Yoon-soo Park has been selected as this year's recipient. And the top 10 representative research achievements of KAIST in 2022 were selected through a process where professors' research outcomes from 2021 and 22 were submitted by departments. Each college prioritized the submissions and made recommendations, which were then evaluated by the research committee. Professor Min-kyo Seo, Jae-uk-an, Chan-hyuk Kim, and Won-seok Chung, Chung Kim, and Hyunju Lee, and Kwang Hyun-jo, and Jung-kyun Choi, Sang-yup Lee, and Ji-hyung Kang, and Hyung-jun Kim were selected for this award. We will make every effort in the future to actively recommend all the professors who are receiving awards today as candidates for faculty awards conducted by domestic and international institutions. We hope that Research Day, the celebration that serves as a platform for researchers, will be a valuable time where diverse and excellent research achievements are widely shared. As we conclude the announcement of the recipients and the background of the awards, we would like to express our gratitude once again to the professors who have devoted themselves to research and achieved outstanding results. Thank you very much.
Next, we will proceed with the awarding ceremony for the research category in commemoration of the 52nd founding anniversary, as well as the presentation of top 10 representative research achievements of 2022. A total of 21 researchers will receive awards, including 1 grand prize winner, 2 research prize winners, 1 innovation prize winner, 1 team for the transdisciplinary prize, 1 prize for the international joint research, 1 Hyunwoo KAIST Scholaristic Prize, 1 creative and challenging research award, and 11 individuals for the KAIST top 10 research achievement of 2022. Now we will invite the president to come to the stage for the award ceremony. When there is a given award, please give us a big round of applause.
We will now proceed with the presentation of the Grand Research Prize. Professor Hee-tak Kim from the Department of Chemical and Bioengineering for Grand Research Prize. The Grand Research Prize is awarded in recognition of your exceptional research activities that have greatly contributed to the development of our university. your exemplary R&D outcomes a testament to the excellence of our institution. This award is presented to you in celebration of the 2023 Research Day. KAIST President Kwang Hyung-lee, May 16, 2023. Next is the Research Prize. The Research Award goes to Professor Pilsung Lee from the Department of Mechanical Engineering and Professor Hyung Myung from the Department of Electrical Engineering. As Professor Pilsung Lee was unable to attend, So Jin Shin will accept the award on his behalf. Professor Pilsung Lee from the Department of Electrical Engineering, in recognition of your outstanding contribution to the development of our university through your excellent research activities and exceptional research outcomes in 2022, Research Prize Award is presented to you in celebration of the 2023 Research Day. The Research Prize goes to Professor Hyun Myung. The same award goes to Professor Hyun Myung from the Department of Electrical Engineering. Next is the Innovation Prize. Professor Hyun Min Bae from the Department of Electrical Engineering. Your significant contributions to the innovation of related industrial fields through technology transfer and commercialization activities in 2022 have greatly advanced the sharing and dissemination of outstanding research outcomes of our university. Innovation Prize is presented to you in celebration of the 2023 Research Day. Next is the Transdisciplinary Research Prize. This prize is being awarded to a group. Associate Professor Yong Woo-sang from the Physics Department, Professor Sang Woo-han from the Chemistry Department, Professor Seung Hwa-yu from the Mechanical Engineering. In recognition of the researchers' outstanding contributions through transdisciplinary research activities that greatly advanced our university, we present this award to you in celebration of the 2023 Research Day. The same award goes to Professor Sang Woo-han from the Department of Chemistry. It also goes to Professor Seung Hwa-yu from the Mechanical Engineering. However, he was unable to attend today's event. Next is the International Joint Research Prize. Professor Song Ho-jo from the School of Computing, he wasn't able to attend today's event, so Min Kim will receive this award on his behalf. In recognition of your exceptional contributions to the development of our university through international collaborative research activities in 2022, this award is presented to you in celebration of the 2023 Research Day. Next is the Hyunwoo KAIST Scholastic Award. Associate Professor Bom Jun Kim from the Chemical and Biomolecular Engineering Department. This award is being presented to you in recognition of your exceptional academic achievements, which have elevated the status of KAIST through outstanding research activities in 2021. Next, we'll present the KAIST Creative and Challenging Research Award.
큐카이스트 창의도전연구상 화학과 조교수 박윤수.
Assistant Professor Yoon-soo Park from the Chemistry Department. In recognition of your significant contribution to fostering a research culture that embraces creative ideas and fearlessly tackles challenges through the research activities of 2022, we present you with this award on the occasion of Research Day 2023.
카이스트 총장 이광형. 다음은 2022년 대표
We'll now have an award ceremony for the KAIST Top 10 Research Achievements. Everyone whose names get called out, please come to the stage. Associate Professor Min Kyo Seo from the Department of Physics, Professor Chae Uk-an from the same department, Associate Professor Chan Hyuk Kim from the Department of Biological Sciences, and Associate Professor Won Seok Jung from the same department, and Professor Chung Kim from the Department of Mechanical Engineering, Associate Professor Hyunju Lee from the Department of Electrical Engineering, Professor Kwang Hyun Cho, Department of Bio and Brain Engineering,
물리학과 부교수 서민교. 서민교 교수님은 참석하지
and Associate Professor Chung Gyun Chae, Department of Bio and Brain Engineering, and Professor Sang Yup Lee, Department of Chemical and Biomolecular Engineering.
경제적 파급 효과가 크고
So Professor Min Kyo-seo was unable to attend, so Dong-ah Kim will accept his award on his behalf. This plaque is being awarded to you in recognition of your outstanding research achievements that has been selected as one of KAIST's top 10 research achievements. Your research has made significant academic, social, and economic impact, demonstrating KAIST's excellence in 2023.
대표 연구성과 10선 물리학과 교수 안재.
The same award goes to Professor Chae Uk-an from the Physics Department.
대표 연구 성과 10선 생명과학과
Professor Chan Hyuk Won Seok Jung, the same award goes to him.
대표 연구 성과 10선 기계공학과 교수 김
Professor Chung Kim from the Department of Mechanical Engineering.
대표 연구 성과 10선 바이오 및 뇌공학과 교수 조광현.
Professor Kwang Hyun Cho from the Department of Bio and Brain Engineering.
대표 연구 성과 10선 생명화학공학과 교수 이상엽.
Professor Sang Yup Lee from the Department of Chemical and Biomolecular Engineering.
대표 연구 성과 10선 문술미래 전략대학
Associate Professor Hyung Jun Kim from the Munsul Graduate School of Future Strategy.
시상해주신 총장님께
Thank you, President, for awarding the recipients. Before he gives the congratulatory address, we will proceed with a group photo of all the award recipients. Award winners, please come to the stage.
잠시 사진 촬영이 있겠습니다. 수상자분들께서는 자리로 돌아가 주시기 바랍니다.
So all the award winners, please go back to your seats.
다음은 이광영 총장님의
Next, we'll invite President Kwang Hyung Lee for his congratulatory speech.
네, 여러분 반갑습니다.
Good morning, my name is Kwang Hyung Lee, President of KAIST. In celebration of this meaningful KAIST Research Day, we are holding in-person event with many participants, and I'm very delighted. Professor Hee-tak Kim, the winner of Grand Research Prize, professors who have achieved outstanding results in many research areas, as well as professors who won the KAIST Top 10 Research Achievements 2022, I extend my heartfelt congratulations and a sincere appreciation. Out of the top 10 achievements that we achieved, I believe we have senior VP included. So I think that we have really objectively assessed the results. And we also have some female winners. We do not have female winners, but I think that was too strict on the assessment. Yes, of course, that makes me feel much better. For the past 2 years, we have strived to realize the vision of future-oriented culture strategy, the KAIST, including KAIST Center for Ambitious Failure, Eccentric Forum, C2 Project, and Gathering for Clash to challenge ourselves head-on without the fear of failure. As a result, with combined efforts of all the professors and students present here today, KAIST was able to achieve outstanding research results last year. As such, Research Day is the day to congratulate and encourage the research innovation that we have achieved ourselves, and also a day that we share the achievements to lay the groundwork for an even more creative and challenging interdisciplinary studies. Going forward, for all our professors and students and researchers, to ensure an environment where they can focus on their studies, KAIST will actively support your endeavors through necessary means, including better research infrastructure and research administration platform. With a view to ensuring sustainable lives and prosperity, let's work together towards innovative research that addresses global challenges and make bold attempts to seek to open up new fields of research. Once again, I extend my warmest congratulations to all the winners, and I also would like to thank everyone who made today's event possible with hard efforts. Thank you very much. Thank you.
총장님 말씀에 깊은 감사를
I'd like to thank our president for his speech.
2022년 카이스트
Next, I would like to watch the
특선에 대한
videos for the KAIST Top 10 Research Achievements in 2022.
2022년에도 많은 교수님께서
Many professors have achieved outstanding research results in 2022, but among them we have selected 10 exceptional research achievements and produced videos to make it easier to understand the research contents.
시청하시겠습니다.
Let's watch the videos. Recently, studies have been conducted on the orbital angular movement of the light, and this is called optical vortex. In this research, we presented a new platform for the spontaneous generation and manipulation of quasi-particle-like OV textures that are dynamic, interacting with an external field. The platform that we developed is called a gradient thickness optical cavity, as the figure here demonstrates the thickness of dielectric materials change in this multi-layered structure. Intriguingly, this system has different topological phases which allow spontaneous generation and extinction of ovaries. This research paves the way for a new path in topological photonic textures in that ovaries can have quasi-particle-like property. Going forward, we expect this research to contribute to the development of active ovaries capable of controlling ultra-high-speed orbital angular moment, as well as research on other topological photonic textures with quasi-particle-like properties. A Rydberg atom is formed by exciting the outermost electron to a nucleus into a high-energy state by using a laser. As a result of Rydberg atom interaction, when two atoms are close together, only one of them is considered as the Rydberg atom, while the other only can remain in the ground state. This is equivalent to creating quantum entanglement state that is essential for quantum computing implementation, so we can use Rydberg atom to implement quantum computing. Our lab randomly arranged about 20 atoms in three-dimensional space to study the problem of combination optimization of graphs, especially the problem of maximum independent sets, and confirmed that when laser is applied to atoms and excited to the Rydberg state, the resultant state is consistent with the maximum independent set problem. Going forward, by implementing quantum superiority that efficiently reduces computational speed compared with existing computers, we expect this result to be how real-life applications help solving various problems that require optimum conditions. Alzheimer's disease is the most common type of dementia, and no cure has been found so far. Alzheimer's disease is known to be caused by the accumulation of A-beta and tau proteins, and a type of antibody called aducanumab was presented by Biogen in 2016, and another called lecanemab recently presented by Biogen and SI have meaningfully reduced A-beta in the brain of a patient. But in terms of cognitive improvement, there were some unsatisfactory aspects. As for antibodies, only microglial cells can have antibody receptors. So the target is removed from microglia, but it causes neuroinflammation during the process. Owing to this reason, a new type of drug was required, but different from existing antibody-based cures, something that does not cause neuroinflammation. For this reason, our research team collaborated with Professor Chanya Kim of the Department of Biological Sciences to create a new type of fusion protein, alpha-A-beta Gas6. The Gas6 fusion technology can be applied not only to A-beta but also other neurodegenerative proteins, as well as autoimmune diseases, where inflammation plays a major role. So it can target other various types of diseases. Our lab simulated the structure of the human skin to implement the properties of human skin into robots. In particular, silicon and hydrogel were used to robotic skin to protect complex three-dimensional features and provide precise tactile senses. This robot skin can protect various tactile senses with high coverage. It is flexible and has healing capabilities, so it can be applied to prosthetic arms and prosthetic limbs through such physical safety. Should this be applied, it is expected to give the same shape and function as the actual limbs to the amputees. Applying these robotic skin to technologies to humanoid robots will enable human-to-human-like tactile interaction between humans and robots, and to safely perform complex movements and tasks. Ultrasound stimulation of the brain is a technology that can non-invasively transmit energy deep into the brain. To find the mechanisms of brain disorders and develop relevant treatments, ultrasound stimulation technology has been actively studied in recent years, and it can non-invasively and accurately deliver stimuli to the brain. However, conventional ultrasound techniques have disadvantages such as large volume, electrical noise, and dependence on anesthesia. To solve this problem, we have developed a system that integrates MEMS-based CMUT devices with EEG electrodes that allow long-term stimulation and simultaneous neural recording of freely behaving rodents. Using this system, we plan to develop various brain disorder treatments in the future. To overcome the limitations of current chemotherapy of killing cancer cells to treat patients, our lab is developing reversion technology that does not kill cancer cells but reprogram the malignant cells into benign cells. As part of this research, we have developed a technique for reprogramming the most malignant triple-negative breast cancer cells into treatable luminal A breast cancer cells.
광암세포로 리프로그래밍하는 기술을 개발하였습니다. 이번 연구는
The study was accomplished through system biology research that combined computer simulation analysis with molecular cell biology experiments. Should the outcomes further develop into a treatment technology, it will open up new treatment possibilities for TNBC patients who currently have to resort to existing toxic chemotherapy treatment. With the recent spread of the COVID-19 pandemic, companies such as Pfizer, Moderna, and others have produced mRNA-based COVID vaccines. A cancer vaccine that applies the same principle is in the spotlight as one of the next-generation cancer treatments. The most important process in making these cancer vaccines is determining the target. Protein fragments that contain mutations in cancer cells and bind to MHC are called new antigens, as they carry cancer specificity that does not appear in normal cells. They make ideal vaccine targets. So the response of T cells is required to a valid immunological target, so predicting immune reactivity is really essential. In this study, to predict whether or not the neoplastic antigen and MHC complex can stimulate the reactivity of T cells, we have developed a deep learning algorithm. This methodology is gaining attention as the first technology to predict the reactivity of T cells. The technology, which is gaining ground in the world as well as undergoing active clinical trials, is expected to be widely used during the key development stage of mRNA cancer vaccines. Lutein is present in the macular lutea of our eyes and plays a crucial role in maintaining our eye vision. In particular, it protects macular lutea and maintains good eye health. Lutein is currently available in the market is extracted from a plant called marigold, but it is insufficient to supply in bulk for many reasons. To solve this problem, our research team applied systemic metabolic engineering. Our team used glycerol, an affordable biomass, as the carbon source, and through metabolically improved strains, we produced high value-added lutein in an eco-friendly and highly efficient manner. Simply introducing lutein by synthesis pathways present in the plants into E. coli does not produce lutein. To resolve various bottlenecks that occur in the metabolic pathway, we applied various metabolic engineering strategies to increase the amount of precursors in the heme coenzyme, including substrate channeling and electron channeling. As a result, we have successfully produced lutein. In terms of enriching humanity and maintaining good health, it is highly meaningful that this metabolic engineering of E. coli or other bacteria opens up opportunities for producing various natural substances. In the future, wearable electronic devices, soft robotics, and other various electronic devices that can be freely changed according to customers' various needs will be widely used. In developing these shape-shifting electronic devices, liquid metal particles have gained much attention. Our research team applied ultrasonic waves to connect liquid metal particles in the polymer and create a network. Based on this, we implemented an elastic printed circuit board technology which can freely change its shape. Through this, we successfully developed various electronic products including flexible displays and medical devices. Existing liquid metal-based stretchable conductors have limitations in the selection of polymers, making it difficult to give various functions. But our technology is significantly meaningful as it overcomes such limitations and can be applied to many different products. Our lab studied how human activities affect typhoons and heavy rain and published the results that human-induced global warming may have an impact on the changes in the frequency of typhoons and heavy rain. We simulated two different scenarios, Earth with human and Earth without human. We calculated the difference in the frequency in the two Earths and obtained data on the tendency where humans induce changes in the frequency of typhoons and heavy rain. We also compared this value to the tendency of frequency change observed in the real Earth. As a result, when humans were present, there was increase in frequency of typhoons and heavy rain in coastal East Asia regions, while the frequency decreased in low-latitude regions, just like the real Earth. Furthermore, in order to prove with numbers that such similar tendency is found because of human activities, we analyzed anthropogenic fingerprint. As a result, while the anthropogenic fingerprint signal stayed near 0 point in the Earth without human, the signal showed a sharp increase since 1970 in the real Earth. So the recent increase in the frequency of typhoons and heavy rain would have mainly affected by climate change, and we concluded that human activity is largely responsible for such phenomena.
영상을 시청해 주셔서
Thank you all for watching the video. And now we are going to watch the video of the award winners of Outstanding Faculty Awards in Research category.
안녕하십니까?
Good morning. I am Sang-Yup Lee, Senior VP for Research. I sincerely congratulate you on holding the 2023 Research Day today. Due to the COVID-19 pandemic, we weren't able to meet thus far, but we are finally able to conduct today's Research Day face-to-face again. I would like to sincerely congratulate the researchers who won the award today and to those who were selected as the top 10 excellent achievers in 2022. Your dedication and hard work are truly commendable. All this time, KAIST has led our nation's economy through innovative research and is becoming a world-class university. In fact, the National Academy of Inventors in the United States announced last week that among the innovative universities registering the most U.S. patents among the top 100 universities in the world, our KAIST has ranked the 12th. And in fact, KAIST has attained the best rank among the universities in Asia. Looking back on the research of everyone who won the award today and those who were selected for the top 10 research achievements, I believe that it has not always been a smooth journey. However, I once again express my respect to all of you for overcoming all those difficulties with creative ideas, indomitable efforts, and achieving great results. KAIST will continue to promote the development of science and technology and put all our efforts to be the leading player in our nation's economy through continuous innovative research and creative challenges. Once again, I would like to congratulate all the award winners today, and I hope that everyone will be able to discover convergence research topics and create opportunities for good research to come through the meeting today. Thank you very much.
The future energy technology will be developed upon two pillars: electrification of mobile power and the expansion of renewable energy. With this in mind, ultra-high energy density lithium metal batteries and water-based batteries with enhanced safety and price competitiveness are emerging as promising future batteries. One of the biggest challenges in implementing lithium metal batteries is to overcome the irreversible side reaction of the lithium metal anode. Our research team has developed an interfacial protective layer, electrolyte, and lithium metal anode that can suppress corrosion reactions between the electrolyte and the lithium metal anode. Through this, we designed a lithium metal battery with more than twice the energy density and more than 500 life cycles compared to the lithium-ion battery. In particular, it showed that the reversibility of the battery can be dramatically improved through the control of the lithium-ion coordination structure and the floating layer of the interface. In order to expand renewable energy, a large capacity energy storage device capable of storing this renewable energy is essential. To overcome the flammable issue of existing lithium-ion batteries, we have developed water-based batteries, and we are developing with fundamental inflammable properties. To this end, zinc bromide, which cost 1/100th of the price of the lithium-ion battery active materials, was used to simplify the battery structure. We implemented a 100 watt-hour non-flowing zinc bromide battery, which reduces the battery price by 1/3 of the existing water-based batteries. The problem with the commercialization of the vanadium redox battery, one of the aqueous batteries for the large capacity energy storage devices, was a vanadium electrolyte, which accounted for more than 50% of the total price. To solve this problem, we have developed the world's first technology to manufacture vanadium electrolytes based on cathodic processes, reducing the manufacturing cost by 40%. This technology has been transferred to domestic company and is currently being mass commercialized. The research on the high performance of lithium metal cells and the aqueous cells through interfacial engineering is important as it presents the feasibility of realizing the next generation battery technology for future energy technologies. I think you will gain insights for good research by talking to many researchers in your field of interest and referring to papers in other fields and related major books. Then you'll be able to gain a very good insight.
전산역학은 기계공학, 응용수학,
Computational mechanics is a field of research that combines mechanical engineering, applied mathematics, and computer science. It accurately implements various physical phenomena covered in science and engineering through computer simulation, or in other words, numerical analysis. Nowadays, with the help of computational mechanics, we can reproduce real-world physical phenomena precisely in a virtual world made up of computer graphics. Our research team focuses on the finite element method, which is called FEM, which is the most frequently covered research topic in computational mechanics over the 50 years in the field of mechanical engineering. In particular, through the study, we succeeded in developing a triangular shell finite element with the world's best accuracy in the field of FEM. This research finding is evaluated to have solved the challenges of the past 80 years. In addition, we invented a methodology called self-updated finite element method, which is a novel analysis technique applying deep learning, and developed a new model reduction technique with an accuracy improvement of more than 100 times over the existing technology. We also developed a real-time strain gauging technique for implementing a highly reliable digital twin representing real-world structures. I am also developing an analysis technique for simulating fluid structure interaction phenomena. In this process, I developed the world's first oil-carbon analysis technique for floating structures and have obtained research results to solve the density non-uniformity problem, which is the biggest obstacle to the SPH technique used for analyzing fluid problems of high nonlinearity. Computational mechanics is a bridge between the real world and the virtual world. In the future, I'm going to try these new ideas to realize a virtual world where physical phenomena in reality are applied more precisely. So the question is that the research is too difficult. What should I do? And the answer is, do not be afraid to challenge yourself boldly with your own vision. And even if you face difficulties in your research, you will succeed if you persistently challenge yourself until you achieve your goals. Students, too, should also get good research results if they constantly challenge themselves with their own ideas. With the goal of robotics for smart cities, I mainly research robot navigation, machine learning for this means, and AI technology. Among them, I focus on research related to autonomous driving, flights, walking, and cluster robots, which are important technologies for future cities. The research that our team conducted this time is the development of robust SLAM technology for autonomous driving. It refers to a simultaneous localization and mapping algorithm, and which is a method of estimating the location of a target within a map while simultaneously creating a map of the surrounding environment. It is a key technology for exploring and developing in extreme environments that are difficult to be done by humans, such as the space and deep sea, by using these autonomous vehicles and equipments. Through this study, we developed a graph-based sensor fusion SLAM technology that is resistant to dynamic or feature-deficient environments. We developed GP-SLAM and DynaVin's algorithms to cope with dynamic environments, and we also developed this ADA-Leo algorithm to cope with environments that lack feature points. Through this research results, we transferred the original technology to the enterprise and jointly won the Innovation Award at CES 2023 and also obtained the second prize in academia at ICRA 2022 SLAM Challenge, which is the largest international conference in robotics. And also in terms of autonomous flights, our team was the only one among the 10 finalists to complete the autonomous flight without any prior information at the Future Challenge Defense Technology Competition. In addition, during the study, we developed a technology through reinforcement learning named Dream Walk, which can walk on stairs and rough terrains with only inertial sensors and joint sensors inherent in robots without the help of visual sensors such as vision or radar. This allowed us to develop more advanced quadrupedal walking robots that can judge terrains and walk without visual sensors. Together with Georgia Tech and ETRI, we have been developing these technologies together to allow quadrupedal robots to move autonomously in dynamic realization environments, which can also be used in orchards and substations. The mobile intelligence technology we're developing is a technology that can be applied to various applications in the future, and it is expected to be actively used not only in autonomous driving, walking, and flight mentioned before, but also in extreme environments and state development that are difficult to be done by humans. So, are there any advices that you would like to share to students? Our lab is conducting studies that can benefit the public while doing research that others do not. I think research does not end with a thesis, but it gains its meaning when it conveys a social impact. And research should be able to benefit the world and not just self-satisfaction. So, developing technologies with economic and social impact and research and challenge yourselves in a way that provides public safety and benefit.
The humankind has been transmitting electrical signals using copper wires for the past 150 years. This is possible because of the small electrical loss due to the free electrons inside the copper wire. But as electricity flows, a magnetic field forms around it, and this field creates an induced current. This induced current becomes larger as the frequency increases, so all the current flowing inside the conductor is offset at higher frequencies, and the current flows only on the surface of the conductor, which is called the surface effect. So, as the frequency increases, the cross-sectional area through which the current flows decreases and the electrical resistance increases. For this reason, the electrical transmission loss of the conductor is small at lower frequencies, but it is large at higher frequencies, which is why you cannot find USB cables longer than 2 meters in length around you. Fundamentally, the conductor has free electrons, which gives rise to this issue and creates a limit to the transmission speed over copper wires, which is known to be near 100 gigabyte bps. To solve this problem, we have developed a technique for transmitting ultra-fast signals using non-conductors without free electrons. According to the basic laws of physics, electromagnetic waves traveling in the dense medium do not go out of the small medium. Using this principle, we make the cable using a sponge that is denser than air. So then, when electrical signals are emitted inside the sponge, the electromagnetic waves travel along the sponge. Since the sponge is a non-conductor and has no free electrons, there is no surface effect of increasing signal loss at high frequency. I named this non-conductor cable EQ. The antenna for signal radiation is made of the lamination process of electrical substrates. So this solution does not contain any parts except semiconductors. So it is very advantageous in terms of power consumption and price. It can transmit up to 5 meters, which is difficult for copper wires to reach in ultra-high frequency areas, and the price is about 10 times cheaper than that of optical cables. We designed and built the necessary semiconductors to demonstrate the performance of this ultra-fast non-conductor communication, and we actually built the E-tube cable and demonstrated that it can transmit signals at 50 gigabyte per second speed of up to 5 meters. This research was published in the 2022 ISSCC, and E-tube cables are being mass-produced by Molex in the US. I usually look for research topics from the practical discomfort I feel in my daily life. For instance, think why USB cables are so short and why there are no faster cables. Then try to solve the essence of those problems from a long-term perspective. So as for our students too, I think you can gain inspiration for research if you read papers to solve problems and people are concerned instead of finding problems.
Hydrogen electric vehicles such as Hyundai Motors Nexo, one of the most important future industrial technologies, are powered by a source called hydrogen fuel cells. And in order for this hydrogen fuel cell to work properly, a catalyst that separates hydrogen into protons and electrons is needed. And these catalysts move electrons that are properly separated to generate electricity, and protons combine with oxygen to release water. And platinum is usually used as a catalyst for the fuel cells, but the price of platinum is so high, which hikes up the price of the vehicles and makes it much more difficult for it to become widely available. And so for that reason, scientists have been continuing to study how to produce a higher performance catalyst using much less platinum. And so that is why scientists came up with an idea, and the idea is to make a catalyst with a structure called a core shell. And this core shell structure can be thought of a well-known snack called a home run bowl. And if you look at the structure of the snack, as you can see, the shell is made of the core is made out of chocolate, whereas the shell is made of the crispy snacks. And so similarly, these nano catalysts are not made just from one platinum, but instead it can be made with a kernel filled by other substances, and only the shell can be used out of the platinum. And this structure is called a core shell structure, and if it is being used properly, we can use less platinum, and also if we can adjust the thickness of this core and shell or the properties, then I think we can make a good catalyst with better performances, even if we use the same amount of the platinum. And if we use this structure to a real catalyst, it is crucial to know what the intersurface consisted of this core and shell looks like and what properties it has in it to maximize the efficiency of this structure. And because the interfaces of the core shell structure are obscured by the shell, it is difficult to accurately look at the interfaces. And so that is why there are several limitations to the study that maximizes the performance of the core shell structure. In this study, a convergence research between the three departments of KAIST, namely the Department of Physics, the Department of Chemistry, and the Department of Mechanical Engineering, was conducted and successfully performed a three-dimensional measurement of the boundary structure between the shell and kernel inside the platinum-palladium core shell nanocatalyst, which was not visible due to the limitations of the existing technology. But this clearly shows that how the catalytic performance of the core shell catalyst is determined at the level of a single atom, and this was only possible with consisting the team of the research of many different departments. And so that is why we were able to successfully achieve this type of great achievements. And so the chemistry department has synthesized the nanoparticles and experimented to determine the catalytic reactivity of the synthesized nanoparticles. And from the physics department, they have were able to look into the atomic resolution, three-dimensional electron microscopy, and examined how atoms are distributed three-dimensionally at the core shell interface at a single atomic level, and discovered how the positions within the interface are distorted by their mutual interactions. And also the Professor Seung-hwa Ryu of the Department of Mechanical Engineering, based on the atomic structure obtained from the experiments, used molecular static simulations to determine what causes the distortion at the interface. In this study, we have identified how boundary structures change the structure of platinum ion on the surface at a single atomic level, and were able to immediately calculate the catalytic performance of the surface by substituting the position of atoms in the structure of surface deformation. Hence, we mapped what the surface catalyst performance is at the single atom level and were able to give directions on how to further improve the performance of the fuel cell catalyst performance. And we were able to also present such directions based on the results of the study. To students who are planning for convergence research, if you need the expertise of other laboratories, first you need to identify their expertise of each lab, and then you should actively contact them and hold this active discussions as well. And most of the professors would positively respond to you, so it will be good to show your proactiveness first. And when you conduct a joint research, the most important thing is that you must have faith, because you need to have this faith and trust in the other person. And if you have the patience to wait, and also if you could actively conduct the research, then of course that you will be able to obtain excellent research results. Even though there are similar concepts in one field and another, oftentimes the same concept is coined or termed differently in different fields. So that is why it seems that convergence research can be much easier to conduct if you always think about how to express the same term in other person's fields.
Our research team is conducting various studies with the vision that the future direction of artificial intelligence will be augmented intelligence. One of such examples is the study of intelligent electronic skin sensors. Skin-type sensors obtain information about human movements while the user are living their daily lives without much feeling of wearing them. However, it is difficult to understand the intentions of the information obtained. For instance, the same movement of the same user may generate different sensor signals, and in some situations, they may have different intentions despite being similar movements. So in this study, we used the motive of learning methods of children to implement an artificial intelligence model properly grasp the intention of users from skin-type sensor signals. Regardless of a particular task, a person can quickly learn a new task by utilizing a learned sense of identity. So that is a sense of movement. So we propose an artificial intelligence model that uses data generated regardless of the specific task to first learn the model and grasp the specific task with a small amount of data. Through this study, we found that it is possible to recognize letters from the action of typing without a keyboard, and also identify object shapes from the action of touching objects using skin-type sensors in our proposed model. The intelligent electronic skin and fast hand motion recognition technologies we have studied are significant as they show the potential for the development of future wearable devices equipped with skin-type sensors that accurately identify user intentions. Many students tend to focus too much on one field of study, so I would like to recommend them to practice looking for answers in various fields with a broader perspective. This study, too, solved the problem by combining the fields of material and AI software, so I believe students would also be able to get good research results should they try to solve problems with such a convergent way of thinking.
In our research team, we concentrate on developing high-performance polymer materials for diverse applications such as organic electron devices, secondary battery electrolytes, and smart particles. Our research focuses on designing materials that exhibit contradictory properties, designing materials with extreme properties beyond what conventional materials can achieve. One of the particular interests lies in the conflicting properties of high electrical conductivity and mechanical flexibility. Materials with high electron mobility are prone to breakage, while materials that stretch like rubber lack electrical conductivity. So, developing materials that possess both of these conflicting properties simultaneously has been considered an important challenge. To tackle this issue, our research team has been approaching it it from the perspectives of polymer material design and synthesis in recent years. Just as the insertion of a spring between rigid high-performance materials provides elasticity, we have successfully developed flexible high-performance solar cells by connecting rigid electrical materials using molecular springs. Specifically, we have reported the world's first flexible solar cells that achieve up to 40% elongation while maintaining 15% efficiency. We expect that this development will contribute to solving the power supply issue, which is an essential factor for future wearable electronic devices. Expanding upon this material design concept, we have also applied it to solid-state batteries. Solid-state batteries can significantly improve battery performances while eliminating the biggest safety concern, which is the risk of fire during electric vehicle operation. The required solid electrolytes must have an extremely high lithium ion transfer rate and also possesses high mechanical properties for stable battery operation. But achieving both of these properties simultaneously is almost impossible. But we were able to successfully develop these high-performance polymer electrolytes and stretch like rubber while maintaining a high lithium-ion mobility, leading to the implementation of high-energy density solid-state batteries. Through this accomplishment, we have secured the essential core technology for next-generation solid-state batteries. So I believe that finding important problems and obtaining solutions cannot be achieved through individual research alone. What I consider most is interdisciplinary research with different topics and a culture of respectful yet occasionally intense discussions. And the solution to this research was able to be achieved through this collaborative research with other departments of the mechanical engineering and electrical engineering and through rigorous debates. And I hope that all students can collaborate and respect each other to identify to solve these important problems by walking with researchers around them. Organic chemistry, which is rooted in basic science, is the study of efficient synthesis of substances like medicines, secondary batteries, and polymer materials. Our lab is developing efficient and eco-friendly source technologies by studying sustainable chemical reactions and catalysts based on organic chemistry. Our research team noted that nitrogen atoms play a key role in most medicines, such as anti-cancer drugs and leukemia treatments. Currently, ammonia is used as a nitrogen law material to synthesize nitro-based medicines, but unfortunately, this ammonia production process inevitably generates CO2. So fundamental measures are needed to solve this problem. Through the creative and challenging program we carried out at KAIST in 2022, we asked the question of how can we find an eco-friendly nitrogen material that replaces ammonia. And by adding high value to cheap nitrogen materials, we aimed at what we called modern alchemy. The next generation nitrogen raw material that we have been paying attention to is the nitrogen gas, which is the main component of air. It is if we use about 80% of nitrogen gas in the atmosphere for organic synthesis, then we will be able to implement eco-friendly and economical technologies. But it is known that the two atoms contained in nitrogen gas form a strong triple bond, making it very difficult to directly use them in chemical reactions. And so we have devised a strategy that uses this metallic materials to activate strong bonds between nitrogen and nitrogen and make them react with organic materials one after another. And through this strategy, we were able to succeed in synthesizing amine compounds. And in the future, we will further improve the efficiency of this reaction and apply it to actual pharmaceutical synthesis or electronic material synthesis. Like an alchemist who tried to turn cheap lead into gold, we will try to realize this modern alchemy of turning cheap air into important medicines. And I think one of the most important points in novel research is active discussion. And while we were debating on this Harvard-Bosch reaction, we were able to gain this idea, and I want the students to also gain inspirations through active debates.
Thank you for watching the videos. Last but not least, we will invite Professor Hee-Tak Kim, the winner of Grand Research Prize, to come to the stage for the special lecture on his research achievements. Please give him a big round of applause.
예, 반갑습니다. 김희탁입니다.
Good morning, my name is Kim
제가 학교에
Hae-tak.
온 지 10년이 딱
It's been
됐습니다.
about 10 years since
학교
I've been
오기
here
전에는
at KAIST.
산업체에서
Before I
14년간
came here,
있었거든요.
I was
그래서
at
많은 분들이
industrial sites. I worked at
산업체와
industrial
학교 중에서
companies.
어떤 게 더 좋냐라고 많이
So many
물어보는데
people ask
당연히
me, is it
학교가 더
better to
좋다라고
work at
이야기합니다.
industrial
왜
companies or
그러냐라고
at the
이야기하면
university? I
학교에서는
say
실패의
university
자유가
because in
보장되어 있는
university
곳이기
you have the
때문입니다.
freedom of
그래서
research.
이제 10년간
So for the
학교에서
past 10
연구를
years,
하면서
while
수많은
I was
실패를
conducting
했는데
many
오늘 이제
researches,
그 중에서 몇 개 안 되는
I also had many
성공적인
failures. But
거에 대해서
today I would like
말씀을
to
드리고자
introduce one
합니다.
of my
오늘
successful
이제
outcomes,
말씀드릴
successful
주제는
achievements that
요즘
I've
이제
made.
많이 관심을 가지고
So the
있는
topic
배터리에
of the
대한
today's
내용이고
presentation is
그다음에 에너지
batteries.
밀도를
And another thing
극대화시키기
is
위한 리튬 금속 배터리에 대한
amplifying the
내용.
energy
그다음에
density
다른
by
하나는
using
요즘
metal
ESS의 안전성
lithium metal
문제를
batteries. And
항상
another
그
thing that I
해결할
want
수
to touch
있는
upon is
축의
the safety
에너지에 대한
issue
내용.
of the
두
ESS by
가지의
using
연구에
aqueous
대해서
batteries.
말씀을 드리도록 하겠습니다. 소개에 앞서
So
저희
before I
이제
go
내용을
into the
간단하게
details,
말씀드리면 저희는
to
이제
introduce my
2차
lab,
전지와
my
연료전지
lab
수전의
studies
기술을
secondary
연구하고
batteries
있습니다.
and
그래서
aqueous
전기
batteries.
화학공학과
So
인터페이셜
electrochemical engineering and
엔지니어링과
interfacial engineering,
머티리얼
and also material engineering. These three engineering are the areas of study that we deal with.
오늘 이제 말씀드린 내용은 배터리의
So the topic of today's presentation will be confined to batteries.
어떠한 방향으로
So, how will the battery industry unfold in the near future? I think it's really important to improve the safety, and some people say that we should use solid-state batteries to ensure safety. Another thing is in expanding the mobility, the driving range of EVs, and with a view to implementing such, we are trying to increase the energy density. In the ESS field, another aspect that we have to think about is having cheaper ESS storage. So low-cost battery application is another area of our research focus. So the topic of today's presentation is expanding, amplifying the energy density, and also ensuring the safety, but as well as implementing low-cost batteries. So many people have heard about EVs. They say that once charged, it can go about 500 kilometers. The driving range is about 500 kilometers. It is not because the energy efficiency has increased, but the amount of battery packs inside the EVs have increased. So when you use energy-dense batteries, you'll be able to reduce the volume and the weight of the battery, so it will be more economical and also efficient. The lithium-ion batteries that are used in EVs, the energy density is about 200 watt-hour per kilogram. In order for lithium-ion batteries to continuously develop, there are some limitations. So, surpassing that 300 watt-hour per kilogram is a mark that we have to challenge and go over. So compared with lithium-ion batteries, if we increase the energy efficiency and energy density, we'll be able to achieve innovative results. And also in the aviation application, when we have lighter batteries, we can also have more applications in the industry. So what we contemplate is how are we going to achieve these goals? I say lithium metal batteries. The LIBs use graphite at the anode, and while using the same cathode, we replace the graphite anode with metal. That is the LMB, the lithium metal battery, and that can greatly increase the energy efficiency. So energy efficiency per weight can achieve about 300. Currently, as for lithium-ion batteries, it uses graphite for the anode. And if we change that with thin lithium metal, we can reduce the weight. And more recently, as for lithium itself, they don't use the lithium, but just the
이 경우에는 500 이상의 에너지 밀도를 달성할 수
current
있는
collectors
가능성도 제시가 되고
and
있습니다.
achieving
오늘
more than
말씀드릴
500
내용은 이 박형의
watt-hour
리튬
per
메탈을
kilogram
이용하는 기술에 대한
is
거죠.
using thin lithium metal.
그러면 리튬 메탈이 왜 어려운가?
Then,
리튬 메탈은 반응성이
lithium metal
굉장히 큰
batteries,
금속입니다.
it is
그래서
very
액체
reactive.
전해들과 만나게 되면은
When in
상부
contact
부반응이 일어나게
with
되어서
the
이런 SEI라는 부반응들이
electrolyte,
이제
it
침적이
causes
되어서
many side
만들어지는
reactions,
레이어를
and
형성하게
it creates a
됩니다.
thin layer.
이는 이제 액체 전해질과 리튬이
When
지속적으로
lithium and
손실되고
the
있다는 것을 의미합니다.
liquid electrolyte
여기
gets in
이제
contact, it
이
causes
배터리
corrosivity.
통반전 반응을 계속 진행을
Here,
시키면
when it's in continuous contact, the morphology here is uneven lithium thin layer that is caused, and it reduces the reversibility. And when the liquid electrolyte is continuously making the side reactions, it increases the internal resistance, and then it causes safety issues. So in order to solve this problem, the key to resolving this issue here is reducing the lithium's reactivity. That's what our lab had thought. While contemplating on this issue, we have looked at the layers and contemplated on the solvation structure that can reduce the electrolyte's reactivity. And as for these parts, in order to implement this into a real technology, we have used lithium-ion conductor, that is ceramic, and polymer conductor. So we have combined them in a hybrid protective layer. So first, as for the interface, the lithium-ion here quickly moves. And for secondly, the lithium-ion here at the interface, when in contact with bulk liquid electrolyte, they have different solvation. It's like as if when you put salt into the water, it dissolves, and the nitro ion is stick to the water molecules. This is as if the water molecules that is salt is stripped apart, so the positive ions are very freely moving within that medium. So this, when you leverage this property, you can suppress the reactivity. So the liquid electrolyte here, you see the solvent and salt anion is detached with one another. So the solvent that is in such state has very low reactivity. So lithium, it can increase the lifespan of the lithium metal interface. So when you apply this, we can use the electrolyte that is used in LIBs and use the same cathode as well. You're just replacing the anode with the protective layer. And as you see here, the graph, the lifespan increases. So the lithium metal uses very thin, 40 micrometer lithium metal. And then you can increase the lifespan of the batteries. And while engaging in this research, I have looked at this more in detail, and you can see here that it is forming a very stable, very even layer here. But on the other hand, for the bare lithium, it is very uneven. So as for the lithium that is underneath the protective layer, it is very uniform. And while engaging in this research, I contemplated that one of the reasons why LIB was so successful is because of the suppression of the side reaction of the electrolyte and the electrode. And you see here the SEI layer. In the solid electrolyte interface, it suppresses the side reaction. And SEI was successful in suppressing that side reaction, so the LIB was successful. But as for the SI layer that is in the LMBs, it has the characteristics of swelling. So the electrolyte and the lithium is in constant contact with one another. So I thought, is there any other ways that we can resolve this problem? As for the primary battery, as for like lithium metal batteries, once it is made, lithium metal does not corrode. It does not have corrosivity for about 10 years. The key here is the SEI layer here because it has a very elaborate structure. So, how can we apply this very elaborate SEI structure into other applications, I thought. So I came up with this method, is using the materials and the substances in the SEI is to dissolve and then restructuring and reusing the same structure into other battery applications. So the interaction between the two materials, we have LIF, which is a very good component of the SEI. It dissolves and then reprecipitates. It goes through those processes. Through those interactions, the SEI has this very dense structure, and over time, you see that the thickness actually decreases over time. In normal electrolytes, when you store that, it is in constant contact with the electrolyte, and then the reactivity increases. However, as for the topic that I had researched on with the protective layer, the thickness decreases. Another thing is lithium fluoride. The material here creates and then changes into nanocrystallite. And such mechanism shows that it dissolves and then precipitates and create this dense structure. So when you apply this technology, you can see that compared with lithium-ion battery, the energy density can increase to 400 watt-hour per kilogram. So in the full cell, it has 400. It has more than 400 cycles lifespan with high energy density. It's one of the world's first outcomes that our lab has achieved. So if you look at other research that are out in the academia, you can see that ours is the very first. Another important area is ESS, energy storage system, because now we have this regulations that falls upon industries to use renewable energy. So it is important that companies come up with a means to use the energy storage system to store renewable energy. Up until now, we used lithium-ion battery. And in Korea in 2018, we have heavily deployed and installed ESS to use more solar cells. And in 2018, the Korean market was the first. Our market was the largest in the world. However, as you all know, because of the battery fire incidents that were very frequent back in those days, the ESS market had seen negative growth. So as you can see here, the world market is continuously expanding, but the Korean market is not being able to grow further. So there's a challenge there. In order to overcome this challenge, we have came up with non-flammable ESS, with an idea of developing a non-flammable ESS. Out of the many battery-active materials, we have turned attention to aqueous batteries that are non-flammable. And out of them, the lowest cost battery that we can use was zinc and bromine.
이러한 배럴이가 상용화 시도가 없었던 건
Of
아닙니다.
course, there were many attempts to commercialize such technology. About 10 years ago, there were attempts to make a flow-type zinc bromine battery. However, such attempts were unsuccessful because the system was so complicated. And even though they used low-cost materials, the system was too complex, so the total cost was too high. In order to tackle this issue, our lab had thought about simplifying the structure, like the lithium-ion battery, and storing the active material within the battery. And we came up with that technology. From the anode active material to the cathode material, we used various materials here and had done a cost-effective analysis. In order to commercialize ESS, the cost of the ESS needs to be below $200 per kilowatt hour. And as for lithium-ion battery-based ESS, it's about when we thought that we had to reduce that mark to lower than $200 mark. The first attempt that we had made is using the bromine in the two anode and cathodes. Within the cell, we had to accumulate the bromine and to capture that within the electrode. And we needed that structure that can capture the bromine within the electrode. And by using this structure that we have here on the screen, we were able to capture the bromine in the cathode, and we were able to create that state. By utilizing this, we thought that we could suppress the dissolution of the bromine. And about 80% of the energy efficiency had to be satisfied. That was one of the requirements. In achieving more than 80% mark was achieved and to be stably operated. We have proven that. Another thing that we thought was using the zinc. As with the lithium metal, zinc has deposition problems, so it has high irreversibility. To resolve this irreversibility issue, I was reading the thesis on aqueous batteries that were written 30 years ago, and there were similar studies done. And it showed the problem of dendrites. And the dendrites goes through the surface diffusion, they accumulate. And so I thought that we need to anchor and suppress the dendrite growth on the surface diffusion. And I thought that we could solve this problem by going through that process. So, but we have simulated on various carbon materials that are out in the market. And we thought that the most strongest binding carbon structure was, as you can see here, the single defect structure had a very high binding structure. The single vacancy defect is something that you can have the one atom out of the structure. And then if you have this structure here, you see the dendrites accumulating and then going through deposition. But on the other hand, by using the single defect carbon, you see the uniform zinc deposition, which all in all increases the lifespan of the battery. So we actually made the cell and operated. We tested that. In the past, the zinc could not go over past 500 cycles, but as a result of our research, we were able to implement more than 5,000 cycles. So we have proven that we could make a zinc-based battery with the highest efficiency.
현재 진행을 하고 있습니다.
So we're making such efforts to commercialize zinc batteries for ESS.
만들어져 있고요.
Zinc bromine batteries are currently have a 100 watt-hour capacity, and we're aiming to have more than 500 watt-hour capacity going forward.
시도를 한번 이제
And we're
해보려고
trying this
생각을 하고 있습니다.
commercialization efforts.
네. 마지막으로 이제 제가
So last but not least, what I would like to mention is that I mentioned that I studied at, and done researches at the industrial companies before.
굉장히 많은 이야기를 합니다.
So I engage frequently with them still.
어떠한 문제가 있는지를 제대로
So I thought that it is really important to define what kind of problems that the industry has.
또한 이제 소재도 중요하고
Material is important. Of course, the designing and the structure is important, but when you combine many different things, the interface that you have as a result, it's an area that is really difficult to comprehend. But if we can really structure that interface in a well-understood manner, we'll be able to have a way forward.
이러한 연구 성과는
The results of our studies
학생들에 의해서
were all able, our lab was able to achieve such achievements thanks to the effort of our students. So taking this opportunity, I would like to thank all our students who are working at our lab and who worked at our lab. And I would like to conclude that today's presentation. Thank you.
Thank you, Professor Hita-Kim, for your exceptional lecture. We would like to extend our sincere gratitude to all the honor professors today for their outstanding research achievements. And with their remarkable contributions, we aspire to cultivate interdisciplinary research and drive KAIST forward with groundbreaking and astonishing research outcomes. The 2023 Research Day event is now concluded. I would like to thank all the participants once again. And for our special guests, we are handing out the souvenirs, so please take them with you as you leave. And also for our special guests, lunch is prepared in the John Hanna Hall, located right across from the Junggeum Hall Conference. Thank you.